Hi, this is Dr. Anjaneya Prasad, Assistant Professor, Department of Chemistry, Institute of Aeronautical. In this session, I'm going to discussing about estimation of hardness by using EDTA method. Usually, this method is nothing but complexometric titration type of method. So, let me know what is the EDTA. EDTA is ethylene diamine tetraestic acid. It is a multi-dentate ligand. So, in previous class, already we have discussed about what is hardness and what is the reason for hardness of water. So, today we are going to determine how much amount of hardness present in the given sample of water by using EDTA method. So, it is a complexometric type of titration method. Here, coming to the principle. So, what is the principle involved in determination of hardness of water by using EDTA? So, hardness is due to the presence of chlorides, sulfides, nitrates, carbonates, and bicarbonates of calcium and magnesium. So, it is determined by using EDTA. We are going to determine hardness of water by using EDTA. So, here coming to the principle that some amount of water we should take it into the conical flask. So, to that add EBT indicator, few drops of EBT indicator. So, aerochrome bractic indicator. So, we had to add few drops of EBT indicator into the conical flask, as well as 2 or 3 drops of ammonium buffer solution also has to be added. So, reason for buffer solution added to the conical flask is the reaction condition is pH 8 to 10. So, at this region only reaction takes place. So, that's why we had to maintain reaction mixture pH range around 8 to 10. So, to maintain this pH of the solution, we had to use buffer solution. So, usually here ammonium hydroxide plus ammonium chloride buffer solution we are using. So, in the presence of at this buffer solution only we can maintain the pH range around 8 to 10. So, when you add EBT and pH and buffer solution to the conical flask, the contents present in the conical flask changes to wine red color. So, that indicates formation of calcium magnesium EBT complex. So, here EBT act as a indicator as well as ligand. So, nature of EBT is nothing but it can act as indicator as well as ligand. So, when you are adding EBT to the solution which contains calcium and magnesium ions at pH 8 to 10, the EBT can bind with calcium and magnesium ions present in the solution. So, that color of the solution is violet color. Now we have to add EDTA to this complex, which is present in the burette. So when you add EDTA to the calcium EBT complex at pH 8 to 10, the EDTA present in the complex, EBT present in the complex is replaced by EDTA and then forms calcium magnesium EDTA complex. It is a stable complex. When comparing calcium EBT complex, calcium EDTA complex is stable complex. Why we can say that calcium magnesium EDTA complex is stable? Why not calcium magnesium EBTA is stable, not stable? So let us see. So we can explain the stability parameter of a complex as calcium EBT and calcium EDTA on the basis of denticity phenomena. Denticity. So what is a denticity? Let us see. Denticity is nothing but tendency to donate lone pair of electrons to the metal forms coordinate covalent bond. So denticity is nothing but tendency of a ligand to donate lone pair of electrons to the metal to form coordinate covalent bond. How we can explain the denticity phenomenon? So if you know the donor centers present in the ligand, then we can predict the denticity of that ligand. So let us see the structures of EDT and EBT. So let us calculate donor centers of EDTA. So here two nitrogens, 1, 2 and 3, 4, 5, 6. So 6 donor centers present in 6 donor centers present in EDTA. That means EDTA can able to gives 6 lone pair of electrons to the metal form coordinate covalent bond. That's why we can say that EDTA act as a hexadentate ligand. Hexadentate ligand. So denticity of EDTA is 6. So denticity of EDTA is 6. So on the basis of donor centers, we can predict the denticity of EDTA as 6. Whereas coming to the structure of EBTA. EBT. So let us see the structure of EBT. So let us calculate donor centers of. Let us check the donor centers of EBT. 1, 2, 3 and 4. 1, 2, 3, 4. So 4 donor centers present in EBT, Ideochrome bracteae. So denticity of EBT is 4. Denticity of EBT is 4. So now we can say that EBT act as a tetradentate. Tetradentate. So EBT act as a tetradentate ligand. So denticity of EBT is 4. So 4 donor centers present in EBT and 6 donor centers present in EDTA. So denticity of EBT is 4 and denticity of EDTA is 6. Now we can say that EDTA act as a strong ligand due to the presence of 6 donor centers. So due to the presence of 6 donor centers, EDTA act as a strong ligand than EBT. That's why when you are adding EDTA to the complex which contains metal EBT, then EBT present in the complex is replaced by EDTA. So it is a strong ligand. So calcium magnesium EDTA is a strong ligand. So which is present in colorless. That is a principle of complexometric method. That is a principle of estimation of hardness of water by using EDTA. Next, coming to the procedure. So it is a complexation in between the metals present in the hard water and the EDTA. So EDTA can bind the metals in this way by acetate functional group CH3COO minus, CH3COO minus, CH3COO minus, and 4 acetates and 2 nitrogens. So whatever metal ions present in the water bind with 1, 2, 3, 4 acetate molecules and with 2 nitrogens. Now coming to the procedure. So before going to estimate hardness of water by using EDTA method, first we have to standardize EDTA. So what is a standardization? Why we should standardize EDTA? So usually EDTA act as a secondary standard. So what is a secondary standard? So we had to standardize EDTA by using primary standard. So let us see the difference between the what is primary standard and what is secondary standard. Then we can get clarity why we should standardize EDTA. So look at this. So coming to the definition of standards. So that is primary standard and secondary standard. The solution made from primary standard substances. The solution made from secondary standard solutions. That is secondary standard. And the solution which is made from primary standard substances, that is primary standard solution. Like primary standard solutions, for example, magnesium sulfate, calcium carbonate. These are the primary standard substances. Our EDTA belongs to type of secondary standard. Now, what is the difference between the primary standard and secondary standard? So, with respect to purity, so purity of primary standard solution is very high. Purity of primary standard solution is very high. Whereas the purity of secondary standard is very less. And reactivity of primary standard is very low, and reactivity of secondary standard is very high. Nature of the standard. So primary standard is a not hygroscopic in nature, but secondary standard is hygroscopic in nature. So hygroscopic means simply evaporate, simply loses their standards like marker weight, etc. That is a hygroscopic in nature. Contamination, with respect to contamination. So in point of contamination, primary standard, very rare conditions it gets contaminated. But in case of secondary standard, it gets easily contaminated. Why? Because due to their stability, reactivity. It is very, secondary standard substances are very less stable. Stability of secondary standards are very less. That's why it is always trying to get stability by reacting with other substances. So ultimately it will be contaminated. Coming to applications. So used to standardize secondary standards and other reagents. Important for specific analytical experiments. Secondary standards are important for specific analytical experiments. So these are the differences between the primary standard and secondary standard. Purity for primary standard is very high. Purity for secondary standard is very less. Reactivity for primary standard is very low. And secondary standard is very high. And nature, coming to the nature, primary standards are non-hygroscopic, whereas secondary standards are very hygroscopic in nature. Contamination, so primary standards are rarely contaminated and secondary standards are less easily contaminated. On applications, secondary standards and other reagents. It is used to standardize secondary standards and other reagents. It is important for specific analytical experiments. So that's why our EDTA belongs to secondary standard. So that's why it has to be standardized by using primary standard. So important application of primary standard is it is used to standardize secondary standards. So that's why where you are using EDTA, it has to be standardized. So let us see how you will standardize EDTA. So to standardize EDTA, so some amount of EDTA is taken into the burette. So it is standardized by using primary standard. Here I am going to take MgSO4. MgSO4 solution is the primary standard. MgSO4 solution is the primary standard. So that solution is I am going to take as a hard water. Why? Because I am calling it as hard water. MgSO4 is the one of the salt responsible for hardness of water. That's why we can call it is hard water. So, and MgSO4 also can act as a primary standard. So that's why we are going to use MgSO4 to standardize EDTA. So coming to the procedure, some amount of MgSO4 or hard water, that is 20 ml, which is taken into the conical flask. Some amount of MgSO4 or hard water taken into the conical flask. So to that add few drops of EBT indicator and few drops of buffer solution. So here what is the buffer solution? Ammonium hydroxide plus ammonium chloride. So why we should add buffer solution to the solution? To maintain pH. To maintain pH around 8 to 10. At that pH range only reaction is possible. So that's why we had to add ammonium hydroxide and ammonium chloride buffer solution. Then the contents present in the conical brass that is titrated with EDTA. So by adding EDTA from burette, so burette contains EDTA. Burette contains EDTA. So initially, color of the solution present in the conical brass is wine red. Wine red color. So color of the solution present in conical brass is wine red. So when you are adding EDTA, the color of the solution is changes from wine red to pale blue color. That indicates end point of the titration. So we have to add EDTA until color change from wine red to blue color. So that is end point of the titration. So volume of standard hot water. Volume of standard hot water. Here hot water is nothing but MgSO4 solution. That is 20 ml. So how much amount of hot water we have taken in conical brass? 20 ml. That hot water is nothing but MgSO4 solution. So 20 ml of MgSO4 solution is taken into the conical brass. So that volume of standard hot water is nothing but 20 ml. The molarity of standard hot water is 0.01. That means magnesium sulfate solution we have prepared 0.01 molarity. So concentration of MgSO4 solution is 0.01 moles. Next, strength of EDTA, that is M2. We don't know. We had to calculate by using simple molarity formula. That is strength of EDTA solution is M2 and volume of EDTA solution V2. V2 is nothing but burette reading. That is end point of the burette, end point of the titration. So the amount of EDTA consumed to change color from wine to blue color. That is end point of the titration. So that is the V2 value, XML. So by taking simple molarity formula, that is V1 M1 is equal to V2 M2. So M2 is equal to V1 by M1 by V2. So by substituting whatever values we are determined in titration, then we can get M2 value. So that is a strength of EDTA. That is a concentration of EDTA. So that is a standardization of EDTA procedure. So after standardization of EDTA, we are going to determine total hardness of water sample. So let us see how we can estimate total hardness of water sample. So to determine total hardness of water, some amount of water taken into the conical brass. So procedure is same. Some amount of water taken into the conical brass. So to that add EBT indicator and buffer solution. What is the buffer solution? NH ammonium hydroxide and ammonium chloride. So the color of the solution present in conical flask is violet. So it is titrated with EDTA until color change. So that is endpoint of the titration. So volume of hard water sample, that is V3. How much amount of water taken into the conical flask? That is 20 ml. Molarity of hard water sample, that is M3. We don't know, we have to calculate. Volume of EDTA conjugate, that is V4. So that is an endpoint of the titration. Strength of EDTA, that is a M4. So M2 is equal to M4 is equal to M6. Why? Because already we have determined what is the strength of EDTA in first step, in standardization steps. So M2 stands for strength of EDTA. M4 stands for strength of EDTA. M6 stands for strength of EDTA. But contents present in a conical flask will be vary, will be changed. So by using formula V3 M3 is equal to V4 M4, from that M3 is equal to V4 M4 by V3. So V4 is the YML into M4. Here M4 is nothing but M2. So that is a concentration of M2. We have to substitute here. So V3. So how much? 20 ml. Then we can get M3 value. So that means strength of EDTA while using hard water, tap water. So hardness of tap water by using EDTA we can determine. That is M3 is equal to some value. So after determination or after estimation of total hardness, next go for permanent hardness. So in total hardness means total hardness is equal to permanent hardness plus temporary hardness. Permanent hardness and temporary hardness. So we know that what is the permanent hardness, what is the which type of sauce causes permanent hardness and which type of sauce causes temporary hardness. So after estimation of total hardness, we can estimate permanent hardness, water. So let us see how we can estimate the permanent hardness of water. So in this step also, first we have to take some amount of water in conical flask. Some amount of water in conical flask. To that add. Before add EBT indicator and buffer solution, we should heat the conical flask. We should boil the conical flask. Why? Because we are going to estimate permanent hardness. So we know that when you are boiling the water, whatever temporary hardness producing salt present in the water will be remains as precipitate. So that's why before going to add EBT indicator and buffer solution, first we had to heat the conical flask. After that, the solution present in the conical flask is filtered and that is transferred into the another conical flask. Another conical flask. So now we have to add EBT, indicator, and buffer solution. So then going for titrator with EDTA. So same procedure. Until we have to add EDTA, current change from wine lead to group. Then by using these formulas, that is volume of hard water sample V5 taken into a conical flask, that is 20 ml, and strength of hard water sample containing permanent hardness, that is M5, we don't know, we have to calculate, and volume of EDTA solution, that means burette reading, ZML, and strength of EDTA solution M6. So by using this formula, V5 M5 is equal to V6 M6, or M5 is equal to V6 M6 by V5, that is equal to ZML into M2 by 20. So permanent hardness is equal to ZML into M2 by 20 into 100 and 1000 ppm. So in this way we can estimate permanent hardness of water. So if you estimate total hardness and permanent hardness, we can simply estimate how much amount of temporary hardness present in the water. So temporary hardness of water is equal to total hardness minus permanent hardness. So already we know what is the total hardness. Already we estimate permanent hardness. Then simply we can estimate temporary hardness. So this is a procedure for estimation of hardness of water by using EDTA, that is a complexometric titration. Here complex will be formed. That's why we can call it is a type of complexometric titration. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.